Okay, so hello everyone. It's an honor to introduce Professor Lawrence Cheuk to be our last speaker. He received his PhD from MIT in 2017 and became a postdoc at Harvard University. In 2020, he joined Princeton University as an assistant professor. So his research focuses on cold atoms and high fidelity detection of molecules. And please join me to welcome Professor Cheuk.
Can everyone hear me?
Yes.
All right, good. So first I want to thank the organizers, especially Bo Ting and Biao for putting together this summer school. And thanks for having me tell you a bit about looking at condensed matter physics, specifically quantum simulation of certain models using AMO experiments. So for today, what I mainly want to tell you about, mainly I want to give you an overview and then a complete overview of some of the capabilities that we can have over quantum many-body systems realized using atomic and molecular platforms. And it will sort of give you maybe a few simple examples that showcase the control capabilities that we have in the context of looking at many-body physics. So let's get started. And this is sort of a view of, at least for AMO experimentalists, how we think of this effort of quantum simulation. So, in the field of condensed matter, we're often interested in interesting emergent phenomena that can be unexpected and really arise fundamentally out of many. And famous examples include, for example, superconductivity and certain forms of magnetism. And this can be, discovered in real materials that you can pick up and work with in the lab. Now, oftentimes when you discover something interesting, you try to gain some understanding over it. Real materials are complicated. We can't really hope to simulate everything exactly. And the idea here is that you can have idealized models that can perhaps capture the interesting parts of physics that you like about these materials. And perhaps if you understand how these simple models work, you can gain some understanding. For example, with high TC cuprates, maybe certain Hubbard models can capture some parts of it. With magnets, you can have prototypical spin models that can, for example, describe the phase transitions between various regimes. So now with AMO platforms, typically we aren't really working with real materials or in this interface. Rather, we are looking at whether we can tackle these idealized models that can be simple to write down but difficult to solve. And this is sort of an idea called quantum simulation that was first pointed out by Richard Feynman, where the idea is that if you can find a very well-controlled system that obeys exactly the set of equations that you want, then you can essentially let nature solve the problem for you. The energy scales can be different, the length scales can be different, but the physics should be the same. And the reason that we like AMO systems is that they're actually very powerful techniques where you can really now completely control every single particle that you have in the lab. So, for example, with Hubbard models, you could use atoms inside potentials that are created with light fields. With spin models, you can use internal states of an atom or a molecule to encode a spin. and then use tightly focused laser beams to hold on to each one of them. And it turns out you can control the interaction Hamiltonian and access prototypical models such as Ising models or XAC models. Now, AMO as a field is actually quite broad, and in terms of experimental platforms, there actually are many. You can have atoms in their electronic ground states. You can have highly excited atoms in so-called Rydberg states. You can have specific atomic species that have very large magnetic moments. You can also have charged atoms in the form of trapped ions. You can have molecules made out of many atoms, and you can even use light and site-specific setups to actually mimic certain condensed matter models. Now, for today, we won't really have time to go through even examples of each of these platforms. So we'll focus on two things. One, and these are actually neutral systems of atoms in their electronic ground states, and also molecules that are neutral. So as an outline of the talk, there'll be 3 parts to this. Most of it will be on the first 2 parts. And first, I'll tell you sort of an incomplete survey of capabilities with some notable examples over the years of doing quantum simulation with neutral atoms. Then I'll talk about, in the spirit of this theme of advanced detection, of a recent development in the past 15 years or so that is still ongoing on gaining better detection and control over these AMO systems, specifically gaining detection and control down to the single particle level. And then at the very end, just for the purpose of giving you some examples of microscopic detection and control and how they can be powerful, I'll talk about something from my group that we've done recently on looking at quantum dynamics and simple interaction spin models. And the point of all of this is really to showcase some of the techniques that we have in atoms and molecules. So let's get started. We'll start simple with the simplest atom. That would be hydrogen. But the next simplest class would be everything in the first column of the periodic table, the alkaloids. So in a nutshell, they all look like hydrogen. You can think of it as a nucleus with a unpaired or valence electron in the outer shell. Now, as you all know, you can put the electron in many different electronic orbitals, and these actually correspond to excited electronic states. Typically, these electronic states are separated with energies of hundreds of terahertz. So as you'll be able to tell in AMO, we often talk about energies in terms of frequencies. So you can always multiply this by h to get the energy scale. In terms of actual temperature, this hundreds of terahertz is something like order 10,000 Kelvin. Now, this energy scale, if you convert it to a single photon, turns out to be somewhere in the visible wavelength. So these are typically optical transitions that you can address with a laser beam. Now, in the lab, this actually is one of the key ways that you can manipulate these systems. The laser light, you can control when it's on, you can control its frequency, polarization, etc., or even your spatial profile. Now, zooming in a little bit further, as we all know, the electron has a spin, but the nucleus can sometimes also have spin. Actually, more often than not, it has a nuclear spin. And as you've learned from Quantum 101, you know that the coupling of spin to angular momentum into each other will give rise to smaller scale structures, so-called fine and hyperfine structures. Now, you can actually have many low-lying hyperfine states where the electron is not excited, and these are actually all long-lived. And if you pick subsets of these, you can actually use this to, for example, encode spin. Typical energy scales here is actually in the RF or microwave domain. So it's typically 100 to 1,000 megahertz. And again, here, instead of using lasers, you can use RF radiation to manipulate what goes on down here. All right, so let's move on. So let's talk a bit about why this optical transition is actually so important for these atomic and molecular systems and what capabilities you can have. The first important thing is that if you have an optical transition, it allows you to actually image particles. So let's consider the following case where I take a laser beam and turn it right on resonance. If I shine it onto an atomic or molecular sample, then these particles are going to absorb the photons that come in and rescatter them. So if you image this on a camera, you're going to see a shadow of this resonant light. And this is so-called absorption imaging. And the idea is that this image, which you literally take with a CCD camera, gives you information about the density as a function of position. So N of R, the sample. So that is one way you can review information. Now, typically in AMO experiments, the sample has to be confined somehow by a track. So if you directly image, it will give you so-called in situ density profiles. But you can actually also access the momentum distribution of these samples very simply by releasing the atoms and allowing them to fly apart. So if you release the atoms, they have some velocity, they'll sort of expand. Now, after a long time, then the position is essentially mapped to how fast they're flying. So again, from the same image, knowing the expansion time, you can get the momentum distribution. Of course, absorption is not the only way you can detect these particles. Another very simple way is to shine the resonant laser beam from the side. Now, the scattered photons are going to emit essentially over all solid angles. So you can just collect the emitted fluorescence due to this excited particle. So if you collect it on a camera, what you see is light coming from these particles, and this fluorescence imaging technique can even allow you to see single particles of atoms and molecules. So that's on detection. That allows us to know that we have the system and we can work with them. Now, the second very important thing with to understand about these systems is how we can manipulate them, their energies, using laser beams. So here, what we'll do is take a laser and detune it from resonance by a large amount. So because it's detuned, it means that I cannot actually excite the particle into the electronic state. So essentially, I get very, very little scattering that affects, for example, the quantum state of the particles. But now you can see that I can get a virtual process where I couple virtually to this detuned excited state and come back. If I do second order perturbation theory, I get an energy shift that is proportional to the coupling matrix element squared divided by the detuning. So this actually allows me a way of changing the energy that the particles see using laser light. So it turns out that this energy shift is proportional to the intensity of the laser, and it also depends on how far you detune. You can make this beam effectively act like an attractive trap, or if you detune on the other side, it will actually be repulsive. Now, because we can shape the spatial profile of light, this actually allows you a very powerful local control capabilities. For example, if you make a standing wave of light, you can actually allow the atom to see a periodic potential. And this can allow you to access, for example, effectively 2D geometries by simply using one standing wave. You get layers. With two standing waves, you can get 1D tubes that allow you for 1D physics. If you actually confine these systems in all directions, then at low enough temperatures, you actually only access a single band, and you can actually look at various types of single band Hubbard models. course, even simpler is that you could take a single laser beam, focus it really tightly so that only one particle fits in. And if you make arrays of these, you can now imagine picking up single particles using these so-called optical tweezers and assembling these many-body systems one at a time from the ground. We'll get back to this in a little bit. The third thing that actually is very important about having an optical transition is that we can actually get these particles of atoms and molecules cold enough where they actually behave quantum mechanically. And this actually has to do with laser cooling. And the idea is actually quite simple. You can operate your laser slightly below resonance. And then this means that if a particle moves fast enough, its Doppler shift can move the particle into resonance in its moving frame. And then it will scatter photons that get kicked back. So in this way, you have a damping force for the velocity of the particles, and they can be very efficiently cooled to low temperatures. Typically with laser cooling, you can already get these particles all the way down to millikelvin, if not microkelvin. And practically, this essentially is the first step in any of these atomic and molecular experiments that deal with quantum simulation. All right, so that's a bit about how you can manipulate these things, essentially always using EM fields and a lot of it using optical radiation. So now let's take a look at the physical setup of these experiments. So typically, in order to do any of these quantum simulation experiments, we actually have to be in the cold/ultra-cold regime, typically nanokelvin to microkelvin range. Now you might think this is very cold, but it turns out that the energy scales of kinetic energy and interactions are also very, very low. Now, in order to keep this system from heating up, it has to be well isolated. So typically the experiment operates in an UHV chamber where essentially it is completely undisturbed. The sample is then trapped using magnetic fields or using laser beams, as I told you about. And typically the way we interact with it is either through lasers, microwave radiation, or we can even apply typically magnetic fields to actually change the transition frequencies. And in addition, you can also use these external fields to tune how these particles interact. I'll go to some specific examples of how this happens later on. So that's the physical setup of the experiment. So now let's talk about how the sequence of an experiment typically works. So unlike with real materials where you can have a sample that you can make repeated measurements over it, with these ultra-cold systems, the operation mode is actually different. We typically start with some sort of laser cooling and further maybe evaporative cooling and create trapped and very cold samples. These samples then are allowed to evolve under the Hamiltonian of interest, which we can tune. And then at the very end of the experiment, we make a measurement. Now this measurement for these ultra-cold samples is typically completely destructive. So the sample is destroyed every single shot. But at the same time, your measurement is really in the quantum limit. It really performs a quantum projective measurement on all the particles. So the way that typically one obtains data is to repeat this entire process over and over again to accumulate statistics. And we'll see in a little bit how this type of approach gives you access to, in some cases, to very useful information. So with that covered in terms of the experimental sequence and some of the capabilities we have, next I'll tell you, an incomplete survey of some of the many body systems that these AMO platforms have looked at over the past 2 decades.
What is the typical time scale for one cycle of this?
So it really depends. If you have evaporative cooling, it can be something like 10 seconds to maybe 2 minutes. If you do not rely on evaporative cooling, the process of laser cooling is typically very fast. So this entire sequence can take something like 100 milliseconds to 1 second. So that's sort of the typical time scale. There are efforts that now that people are starting where you can reuse the sample of whatever's left over of it, try to reinitialize it, and that potentially can even push some of these cycle times higher. So again, statistics is quite important, and one of the things to point out about typical AMO platforms is that the number of particles is actually not very large compared to the solid state. We don't have 10 to the 23 particles. Typically, we might be working with as low as 1 or 2 particles. Many body, often in some setups, could be anywhere from 50 to maybe 10,000. So that's sort of the range of many body systems that we're talking. And you can see that when you get down to 10-ish particles, statistics become quite important. So being able to repeat this fast will be crucial. So now let me move on to talk about some examples that are notable in the past 2 or 3 decades. And I will essentially follow this in chronological order. So really this field of quantum simulation with atomic and molecular systems really started back in 1995, when the first Bose-Einstein condensates were made using alkaline atoms. Essentially back in the 80s, people in AMO pushed on this frontier of laser cooling, asking the simple question of how cold can you get? Now it turns out that most atomic species actually are bosons. And as we all know, even if you take non-interacting bosons and you go to low enough temperatures, you can get sort of a statistical mechanical phenomenon of Bose-Einstein condensation where a macroscopic number or fraction of your system occupies a single quantum state. So this sort of was a goal in the early 90s, and by 95, people were able to see these first species. Now, in BCs, you will often see this prototypical picture of this thing showing a very sharp peak. And what actually is typically shown here is a time of flight image that shows you the momentum distribution. Essentially, this very sharp peak in the center gives you a bimodal distribution and indicates that a large fraction of your particles actually are occupying the same spatial mode. Of course, this BC was really important because it sort of gave us first time a new phase of matter and also opened the door to looking at what happens with these really pristine samples of particles. But now you might say, BC itself doesn't really require interactions. It can be thought of as purely as a statistical mechanical phenomenon. So something a little bit more interesting and can be thought of as a phase of matter is when you look at BCs or bosons actually with interactions. So in 3D at low enough temperatures, you actually will get superfluid bosons. Of course, it's not so easy to just look at momentum distribution to show that you have superfluid. So now, one of the key experiments to actually establish superfluids of these ultracold-bosonic samples was actually by effectively applying a magnetic field to these bosons. And the way that this was done was actually by rotating the sample. Turns out that for these neutral particles, if you rotate them and go to the rotating frame, essentially you will see an effective magnetic field. And because the superfluid has a phase stiffness, what happens is that all this effective magnetic field has to go through these vortices. So in these images taken with absorption back in 2001, people were able to see these formations of vortex lattices when you stir these bees. And just to tell you a little bit about the technical part of how this was actually done, essentially you could make your BEC, and what they did in this experiment was take two repulsive beams that are tightly focused, and then you could dynamically stir the sample simply by rotating the position of these beams. Then if you allow the system to thermalize, then these vortex lattices appear. So this sort of established that indeed we can now start thinking about superfluid phases in these things. So now this actually leads us into this topic of controlling interactions. So you could see that the superfluid required interactions. So you could ask, how do atoms actually interact at low temperatures? So for these bulk gases, typically the origin of the interactions is when two particles collide. So if you plot the energy of two atoms coming close together, typically it looks something like that. At long distances, you get van der Waals interactions that go as 1/R6. There's something that happens at close ranges. Now, one thing to note is that for typical samples of these ultra-cold gases, the particles are actually spaced much further than any of the stuff that happens at close range. So it means that you could really ignore all that short-range detail and replace all of this by a pseudo-potential that describes the scattering process. Now, if you get cold enough, and you think about a scattering problem where you have free particles coming in and coming back out, then you could see that the only relevant channel that is preserved is the S-wave scattering channel. If you're in scattering channels that have higher angular momentum, there actually is a centrifugal barrier that prevents it. Now, if you have a pseudo-potential and you only have S-wave scattering, you can actually parameterize this all by one number called the scattering length. Effectively, it gives you the size of the scattering cross-section. But now what do we know about square wells in quantum mechanics? If it's deep enough, it can actually support a bound state in 3D. And it turns out with atoms, these bound states are actually molecular states of two atoms at short ranges. And it turns out that you can tune their energies simply by using a magnetic field. So this means that you can move these states around. And it turns out that the scattering process, the phase that you accumulate, or the scattering length, is essentially completely determined by how far away this bound state is relative to the threshold. So essentially, this gives you a knob of tuning how two particles scatter elastically. And these are so-called Feshbach resonances. So when the bound state is right at the threshold, you get a diverging scattering length, or you get interactions that are as strong as possible. If you go on either side, you can get attractive or repulsive interactions. You can even make these particles non-interactive. So this actually is a very useful knob in the context of these bulk gases of atoms, and these Feshbach resonances actually were first observed in the experiment shortly after realization of BECs in the Kelly group in '98. So now, since this is a condensed matter summer school, you might think that, maybe what we want to do is actually look at something that's closer to real materials, where often the properties are determined by what the electrons do. And so we all know electrons are fermions. So then in the late 90s, people started asking the question, instead of bosons, can we actually make fermions and actually get into this quantum degenerate and many-body regime? And that in the late 90s, people were able to first get to temperatures well below the Fermi temperature. Of course, if you convert it to what the typical scales of a real material, you would say that this is still very hot. At least it is below TF and can be considered degenerate. Now, more interestingly, we can ask about what happens with interacting fermions. So now, because of quantum statistics, if you have fermions of the same species, their two-particle wave function has to be antisymmetric, which means that at low temperatures, there is no S-wave scattering. But you can actually pick two species of fermions or two hyperfine states of a fermionic atom. And then they can actually interact via S-wave collisions. Now, using the tool that I told you about of tuning the scattering properties using a magnetic field, or using so-called Feshbach resonance, now you can actually tune the interactions between a two-component Fermi gas. Now, if you look at this simple model of interacting fermions that actually have tunable interactions at very close distances, it turns out that in the attractive side, and when you go very far out, and you go to very low temperatures, this actually will lead to Cooper pairing, so it will give you a BCS superfluid. Now on the other side, if you tune past the resonance, these two particles will actually go down into this molecular bound state. If they get very tightly bound, two fermions become a boson, you can actually get a BC of molecules. As long as these bosons interact, we know that they'll form a superfluid. So this actually opens you up to this area that was actually extensively explored in the 2000s and 2010s on fermionic superfluidity across this so-called BEC-BCS crossover. So the cartoon picture is a little bit like that. On the BCS side, the interactions at low enough temperature allow Cooper pairs to form, one of spin up and one of spin down. And then you can tune essentially the size of the pair to reach this BEC level. So sort of historically, one of the important first experiments was actually to go in this tightly bound limit and actually observe superfluidity, not of the individual fermions, but of these tightly bound fermion pairs. And this was done sort of mid-2000s. So this shows condensation of these fermion pairs. But what about the superfluid? So again, using the same technique that I told you about of stirring and imparting rotation or effective magnetic fields, by 2005, people were actually able to show that across this entire BEC and BCS crossover, tightly bound pairs and sort of long-range Cooper pairs, you can actually show that the system does form vortex lattices, showing that indeed you have superfluidity. And one of the notable features is that right in between where the interactions are strongest, you actually get extremely high superconducting transition temperatures that are as high as about 0.2 TF. So now, of course, these systems are at ultra cold temperatures of several hundred nanokelvins. But if you translate this back to your room temperature, to your real materials, 0.2 TF, would actually be well above room temperature. So this is only possible because you're able to get these interactions very high. And this BEC-BCS system actually has been a very useful benchmark for comparing experiments with theory, because it turns out that strongly interacting bulk fermions are also a very difficult problem. Yeah.
So in this quantum gas setup, is it possible to do some transport measurement? Can you measure viscosity and something like that?
Yes. So transport, I think, has been done, but I think viscosity hasn't been, to my knowledge, maybe measured directly in the transport measurement, but you can actually use extracted from various thermodynamic measurements also. The issue with transport, which actually has been done in ultra-cold experiments, is that typically the sample sizes are not very big and the system is very isolated. So then as you start transporting, the reservoirs or the contacts actually change. But you can still extract, for example, transport coefficients out of these systems.
So the most conclusive signature to demonstrate that one is in the BEC or the BCS limit is just by imaging the vortex lattice. So is there a better way really have superfluid or superfluidity, yeah, what is the most conclusive way to see it in a?
So there's several ways. One is, I would say this is smoking gun. The other way that people have done is to drag laser beams through the system. So then essentially what you see is that as long as the disturbance is slow enough, you don't see any heating. And then there's sort of a hockey stick rise of the heating. Essentially, below the critical velocity, you actually don't excite the system. You can use that as a measure. But that, that actually has been done for 2D Bose gases. Okay, so that's maybe all I want to say so far about bulk gases. So we'll sort of, again, chronologically move ahead with quantum simulation experiments and start looking at what happens when you put particles inside these periodic potentials that are made with standing waves of light. And this sort of was started again in the 2000s. So as I already told you earlier, with light beams, you can, standing waves of light, you can get these periodic potentials. And as we all know from Bloch's theorem, you can get essentially band structure. Now, the important point to note is that with these ultra-cold experiments, they're essentially always in the lowest band. So now let's start again historically with bosons, because it turns out bosonic species are easier to work with fermionic ones. So if you have bosons all in the ground band of an optical lattice, the model is actually quite simple. Particles can hop between neighboring sites with strength J. There might be an on-site energy shift. You can think of this as a chemical potential locally. And then there's another term that essentially is an interaction energy that depends on the number of particles that you have on the site. So now you could imagine that if you have lots of tunneling and very weak interactions, the particles can delocalize, and what you'll get is that you'll be in the superfluid phase. It sort of maps essentially to the lattice version of the BDC. But now when the interactions are actually very strong, then you could see that just to add another particle takes a lot of energy that goes as u and n squared. So essentially you will get, if you try to change it, if you try to add particles and you change the chemical potential a little bit, nothing really happens to the mean density. It stays with n equals 1. So you get plateaus as a function of the chemical potential. Now, typically with atomic samples, they're always held in some sort of trap that can have some shape to it. For example, often they're harmonic near the bottom. So essentially, the density is going to vary. So if you have strong enough interactions, what you should see is plateaus with 1 particle per site. And then as you go further in, they'll jump to 2, and then 3, and so on. So you get this sort of wedding cake structure, even though the trap is. But of course, back in the 2000s, people weren't able to actually see this directly because the experiments didn't have enough spatial resolution, and the samples were actually typically very small. But now they can actually still see this superfluid to Mott insulator transition by doing the following thing. You simply release the system out of the optical lattice, allow a time of flight, and then look at the momentum space picture. If you have a superfluid, then what happens is that you actually get interference terms at interference peaks and momenta that are spaced by 1 recoil of the lattice. But once you enter the Mott insulating regime, phase coherence is sort of lost across the system, and these peaks disappear. And sort of one of the landmark works was actually in 2002 when people were able to see this transition in bosons. And notably, they can go back from the Mott insulator to the superfluid and see these peaks So now let's get to something that has more to do with electrons, and let's replace the particles with fermionic atoms with two flavors, up and down. And this sort of gives you this single band Fermi Hubbard model, where again you have a tunneling term, you have a chemical potential term, and you also have an interaction term. Now, because there are fermions and you're in a single band model, you cannot have two fermions of the same species on the same site because of the Pauli exclusion principle. But if you have one spin up and one spin down, you can still put them on the same site, but they will have this interaction energy. So now it turns out this Fermi Hubbard model, there's a simple single band one on the square lattice, actually has a lot of interest in it theoretically because it's believed to capture at least some of the physics of these ITC cupric materials. Now, experimentally, well, people have various ideas of what the phase diagram should look like. So essentially, if you change the density or the doping, you can go from, antiferromagnet at low temperatures to perhaps maybe superconducting phase. But for experiments, typically, the temperature is always a challenge, and most experiments in the early days were well above this interesting region where you can see these competing phases. But now let's talk about, at least still at high temperatures, what you would see. So if I turn off the interactions, it's pretty simple. I can get a metal if I don't fill up my band. Spatially, it looks like particles of up and down randomly occupying the lattice. Now, if I keep increasing the number of particles, I can actually fill up the entire band with 2 particles per site, and I get sort of a boring band insulator. But I can also turn up the interaction such that it's very costly to have 2 particles on the site. And then I get this interaction-induced insulator, a so-called Mott insulator, where I have 1 particle per site. Now, if you go to this Mott insulator with 1 particle per site and go low enough in temperature, what you'll actually see is actually the spins start ordering. And this actually comes from a super exchange process where if you have 2 spins that are anti-aligned, the energy is more. So now let's ask, in these AMO experiments, where we put these fermion particles into square optical lattices, can we just see these prototypical simple phases? For example, just this incompressible Mott insulating phase. So again, in the 2000s, people couldn't really see this directly, but what they can do is actually change the confinement and try to squeeze the sample. Now, the Mott insulator is incompressible. So it means that if you see some sort of kink in the size as you try to squish it, then that actually can be used as a signature to see this Mott insulator phase. Essentially, you squish it, you keep tightening the confinement, but the size doesn't decrease. So this signatures of these Mott insulators was first seen a little bit before 2010. And you can even go further without local resolution to try to detect some sort of magnetic order. I won't go into details on how this was done. It was sort of a heroic effort, but without local access, these experiments were actually able to see some hints of short-range antiferromagnetic order inside Mott insulators. So this gets me into the middle part of the talk, which is what has happened since then, and what does advancing detection do for us. So now, starting in 2010, there was a very new powerful technique that allows you to actually peer into these systems at the microscopic level. And this so-called quantum gas microscopy. And this is quite important. If you can see every single particle inside a lattice, it means that you can access the physics actually at the shortest length scale, which is 1 lattice site apart. And now, what can be very powerful is that you could start looking at correlation, spatial correlation functions on your system. And oftentimes, if you can't access very low temperatures, just from short-range correlations, it can actually provide hints of what is going to happen or the competing phases that can occur at low temperatures. So back in 2010, this field of quantum gas microscopy first started with 2 experiments, one in Harvard in Marcus Greiner's group and one in MPQ, Mann and Bloch's group, where they were able to see these single bosonic atoms inside these square lattices. Then about 5 years later, people were also able to do this for fermionic atoms, essentially being able to look at Fermi-Hubbard models at the single particle level. So now with bosons, once you have the single particle resolution, then you can really start seeing if you can see this shell structure locally. And this was actually first done almost immediately after the quantum gas microscope was invented. So what you see here, every square box is one lattice site, and every bright dot means detection of one atom. So it looks a little bit irregular, but what you can see here is a plateau of just exactly one particle in the center of the trap. So imagine that there's a confining potential around the center region. Now, if you start increasing the atom number by putting more particles in there, you still see this region, but there's a dark one inside. And this actually corresponds to n equals 2, because it turns out that in these quantum gas microscopes, if you have 2 particles, they actually go dark. Particles are always lost pairwise if you try to image them. Now, if you get more particles, you see an n equals 3 plateau and n equals 4 plateau, and so on. So now this is sort of direct evidence of seeing this not insulating phase. But now let's move to fermions and ask if we can see these insulators in metallic phases. And the long story short is that indeed you can. So if you look at a metal, it looks sort of disordered, nothing very special. If you start adding more particles, you can actually see this empty region appear, which corresponds to an n equals 2 band insulator. You can sort of play with the confinement and actually access large n equals 1 insulators. And of course, beyond density ordering at lower temperatures, what is interesting is actually to see whether the spin state of these fermions actually start forming anti-ferromagnetic order. And the way you can do it in AMO systems, there are different ways, but one way is just to remove one of the spin states and imaging the remaining ones. And you can sort of see here an image where you can almost see a checkerboard pattern where every other site is occupied. So this essentially shows you that you have short-range AFM order. You can also see it in these types of images. And now once you have this, you can start looking at how the range of these magnetic correlations, how they vary with temperature and doping. So now there's actually lots of work since these microscopes were invented on this Fermi-Hubbard model, on looking at the correlations. But in the interest of time, I will just be very brief about what the current directions that are very exciting that people are looking at. So one is to, instead of looking at spatial correlations, is to combine it with some type of spectroscopy using ARPAS-like techniques. This really now can allow you to both get spatial information, but also be able to measure spectral responses. Now, one of the key long-standing challenges in these Hubbard models is actually getting to lower temperatures where you can start maybe discovering new phases of matter. Turns out theoretically, also when you get to low temperatures, things actually get more difficult to predict. And recently there's been some exciting progress where people have gone from just at the tip of seeing magnetic order to maybe entering the regime where perhaps they might be able to see stripe phases or other, who knows what competing phases down here. So that's quite exciting because the field had been stuck sort of here for about 10 years or so. Now, the other very exciting direction is actually going beyond square geometries. For example, recently here in Wasim Bakker's group, and also in Marcus Griner's group, people have started looking at Hubbard models on triangular lattices. Now, the triangular lattice is actually quite a different beast than the square lattice. It's naturally non-bipartite. And it also actually shows a bit of frustration. And recently in these works, these two groups actually saw a new kind of magnetism that only happens in the triangular lattice that actually has to do with a kinetic mechanism. Essentially, by having holes or double bonds, you can actually get tunneling scale type mechanisms that give you either ferromagnetism or anti-ferromagnetism nearby. So now I start this section by telling you that this sort of is an era of microscopic detection. But now another very important aspect that has sort of appeared in the past maybe 7 or 8 years is the ability to microscopically control systems in addition to detecting every single particle. And this actually first started with atoms and uses this very powerful technology called programmable optical tweezer arrays. So optical tweezers are just really tightly focused laser beams. And the programmable aspect of these systems are the following. You can take one laser beam, send it into an optical device that you can control with your computer. One way to do it is to actually use same technology that you would have in this projector. And you can convert this single laser beam into many, many different traps, which can actually be even moved dynamically using your computer, even in the middle of the experiment. So now, back in 2016, people were able to just pick up single particles and assemble them into various geometries that they like. But now, as I said earlier, atoms typically don't interact, and the ground state don't interact until you bring them very, very close together. Typically, if you take two atoms in separate optical tweezers, they actually completely don't interact. So physics would be quite boring if you just have a bunch of interacting particles in various geometries. So what people actually have done was actually to promote these atoms into highly excited atomic electronic states, so-called Rydberg states. And it turns out that once you get to these Rydberg states where the orbit of the outside electron is very big, these Rydberg atoms can actually interact very, very strongly, even when they are separated by microns distance. Of course, there's a fundamental limitation. These Rydberg states are excited, they will fall back down. But typically, the interaction is something like 100 times faster than the lifetime at typical spacings and states. So you can already do a lot of physics with these Rydberg arrays. Now, this approach of highly excited Rydberg atoms inside these programmable optical tweezers have really exploded this field. And there have been lots of work in the area of quantum computing using this programmability and control. Also in quantum metrology, and also some work on quantum simulation of various types of models. Now, let's talk a bit about what types of models you can simulate with these tweezer arrays. Now, of course, you could say if you can build a universal quantum computer, then you can do anything that you want. But that is, pretty far in the future. So let's get back to something that people can do right now. So one thing to note is that if you zoom into these optical tweezer systems, the particle never leaves the tweezer track. So all the information and degrees of freedom has to be stored in the internal states of the particle. So naturally allows you to look at various types of spin models where the interaction essentially couples the internal states. Now, one of the very powerful possibilities with these tweezer platforms is that you can do arbitrary geometries. You're not confined to things that you can make by interfering simple laser beams. The other thing that is interesting is that you can start thinking about doing digital simulation, where essentially you have discrete steps of Hamiltonian evolution. And these discrete steps can even include moving the particles around to change the connectivity of the system. And this can be quite powerful. The second aspect that is quite powerful with tweezer arrays is that you get access to more observables. Of course, you get the same microscopic snapshots, just like in quantum microscope experiments. But the other thing you can do is that you can actually use local gates to actually pull out a little bit more information. This can allow you to measure in different bases. And this is also connected to the idea that this also opens up new ways you can prepare complex many-body states. You can essentially apply gates between a bunch of particles, maybe coupled to an ancilla, which done recently in this work. And then you can actually make measurements on subsets of these particles. Then conditioning on what the outcome of these, this can actually project you the many-body state into the sector that you're interested in. So in a sense, with quantum simulation with these tweezer arrays, we're sort of just scratching the surface of what is possible. So now in the remaining time, instead of going into detail in these experiments, I want to go to a specific example of something we have done recently in our lab. And the focus here is to give you some examples where the advanced detection and microscopic control capabilities allow you to see some simple but interesting dynamics in interacting spin models. So in our lab, instead of using Rydberg atoms, which can decay and actually are pretty hard to trap in these interacting states, we actually use molecules instead of atoms. The plus side is that these molecules, you can put them into interacting states that practically live forever. They're not fundamentally limited by spontaneous emission. The price you pay is that, well, and you should use a polar molecule so that they interact even when they're in different traps via the dipole interaction. The price you pay is that typically the interactions are much slower than Rydberg's. So you can run up against other technical limitations like coherence times or vacuum lifetimes. But nonetheless, fundamentally, this can be quite a powerful platform. So let me go into a little bit about what we specifically use. In the beginning of this talk, I told you about the structure of atoms. I told you about electronic states where you change the orbital of the electron. I told you about what you can get with spins interacting. But now with molecules, you actually get a lot more complexity. The simplest molecule has vibrations, which are at lower energy scales. It also has rotations. When you quantize these, you get a bunch of vibrational and rotational states. Specifically, you can work with low-lying rotational states, typically at sort of 10 gigahertz scale energies, and essentially live forever. You can encode a spin up and spin down system here. Now, the second important point is that with molecules, as long as you pick a generic one that is not too symmetric, it has a dipole moment. As we all know, if you have two electric dipoles, it will interact with interactions that fall as 1 over r cubed. And there's also some anisotropy depending on how the dipoles fall. And it turns out that with these molecules, over the past 2 decades, people have many proposals of how you can sort of, in an analog fashion, natively realize a variety of interesting many-body systems. So I emphasize this as analog, just like how Fermi Hubbard models are analog simulated with actual particles and lattices. So this sort of is near-term possible. Now for today, let's talk specifically about the type of interactions that we'll deal with. So what I'll focus on is specifically 2 states in the molecule that under the electric dipolar interaction give you an effective spin exchange Hamiltonian. So if you have two particles, one spin down and one spin up, the dipolar interaction actually allows the up-down configuration to go to down-up resonantly. This is simply written as S6, S6 plus SY, SY with a prefactor that depends on 1/distance cubed. So the so-called XX model. So now let's get to simple physics that you could do with these interacting spins in simple 1D geometries. Now, if you look at the XX model, it turns out in 1D it's actually not very interesting because you can actually map this to non-interacting fermions and completely solve the problem. So to make the physics a little bit more interesting, there's sort of a digital simulation technique that one can use. And here, what we actually can do is do some type of Floquet engineering. The idea is the following. If my native interaction is XX plus YY, I can allow the system to interact for some period of time in this frame. Then I can rotate all the spins by 90 degrees. So then I'll have YY plus ZZ interactions. I can allow it to interact for Y. And then I can have ZZ plus XX by applying another rotation. Now, if I apply these periodic rotations and I do it very rapidly, this is essentially a type of Floquet driving, then as long as I do it fast enough, the system should be described by the average Hamiltonian. We can think of this as a Magnus expansion, this Floquet drawing. And this allows you to essentially have tunable models of XX, YY, and ZZ interactions simply by modifying what pulse you engineer. So now you have access to XXZ and also XYZ models. Yep.
So can you explain again why there isn't a native method to directly implement XXZ?
So there is a native method. You can apply an electric field to polarize the particles. Then up will have a different energy than down. But that has its own technical limitations. Now with this Floquet method, this can be done very quickly, so you can even quench your Hamiltonian immediately, simply by reprogramming the pulse. So now, just to sort of connect with this idea of digital quantum simulation, one way you can think of this is that each Floquet cycle is essentially a unitary. And what we are actually trying to do is that we're trying to make these XXZ and XYZ models. And what we're doing is actually trotterizing the Hamiltonian into these Floquet blocks. And one of the advantages of this molecular platform is that we can actually do this extremely rapidly relative to the native interaction time scale because the interactions are slow. So you can really do good digital quantum simulation. Of course, the downside of molecules is that they are complicated, and just getting them cold actually was sort of a decade-long effort. But by now, people can make them cold using laser cooling. And in the past few years in the field, our group and others have actually now been able to control single particle properties pretty well, put the particles where we want, and also importantly, control how two molecules interact. And by now, we essentially, at least qualitatively, have all the building blocks for quantum computation and definitely for simulating these spin models. So let's get on with how these experiments actually work. So this is sort of pretty similar to the generic procedure that I told you earlier on, but let's focus on tweezer systems. So typically you do some sort of cooling, then you can get these particles into these tightly focused laser beams. So it turns out that this process, whether you use atoms or molecules, is always stochastic. So you can have a trap regularly, you can have a series of trap regularly spaced, but you only probabilistically get particles. So every shot will be a random pattern. It turns out you can just check where the particles are and just rearrange them into the system, into the configuration that you want. Then there's some other preparation steps, but at the end of the day, you can then evolve under the Hamiltonian of choice. For us, it's these Floquet engineered Hamiltonians. And then at the very end, we essentially read out the internal state of the particle, because that's where the information is encoded. In other words, specifically, we'll read out population and up and down. So now let's take a look at simple physics that one can see in these XXZ and XYZ model. So we'll start by looking at XXZ models, because that's a little bit simpler. So you can think of the XXZ model as composing of two terms, one that exchanges spins, and then there's this Ising interaction. So if I think of the completely spin down state as a vacuum and think of spin up excitations, you can think of the first term as allowing hopping of these spins that are a little bit funny and long ranged. The second interaction just tells you the interaction energy that depend on the relative alignment of two spins. But the important point is that this model can only move spin-ups around at sort of total SC. It can't create extra excitations. So the simplest experiment we can do in these systems that are well beyond mean field and sort of non-equilibrium is simply by flipping one spin and seeing how it propagates. So no surprises in the XX model. This spin will just perform a quantum walk due to these hopping terms. Indeed, in the experiment, you can see in the average spin density, the excitation in the middle of the chain moves around the system and bounce off the walls. So that's relatively simple, effectively single particle physics. But now let's get to something more interesting that really leverage the capabilities of the tweezer platform. So now let's look at what happens, not in the single Magon sector, but let's look at the two Magon sector where two spins are flipped. So we can ask a very simple question. If I flip two spins next to each other, as time evolves, do they fly apart or stay together? And it turns out that if you turn up this Ising interaction very strongly, as long as the interactions are local enough, you actually get an emergent domain wall conservation law. So this means that the two spins have to move together. Now, if you were only able to access average observables, nothing really very interesting happens. So here's sort of some experimental data. We flip two spins in the middle of the chain of 8 and ask how the spin propagates. Now, as I turn out this Ising term, you can see that nothing really special happens. What I really want to see is clear signatures that the two particles move together as a pair. But now with these tweezer systems, what you can do is actually look at every individual snapshot. So you can take the measurement outcome of a single shot and ask how far apart are the two flip spins. At time t equals 0, they were started one side apart, so my histogram just has a bright spot at separation of 1. So I can see that as long as the Ising interaction is strong, indeed, the two spins actually stay bound together and move along. So there's more interesting things you can look at, like how fast they propagate and whatnot. But the message that I want to tell you is that by looking at these individual snapshots, you can sort of directly see these bound states that otherwise would not be possible directly with average measurements. Now, just to give you, one final example of the power of seeing snapshots. So we can ask about something related. So instead of asking what happens if I put two flip spins in my system, I can ask, can the system dynamically generate these pairs out of the fully polarized vacuum state? And it turns out, simply by making Jx and Jy different, you can actually do this. And as I told you earlier, with this flow K engineering system, we have full control over the strength of these. And the way to see this is as follows. You can rewrite X and Y as plus and minus operators, and you get a term that has two pluses and two minuses, meaning that from a spin polarized state, you get pairs that get created out of the vacuum. So one way to understand this is actually to map this to fermions. You can actually map this directly to an interacting cation chain. And this process is nothing more than two fermions becoming a Cooper pair and decreasing the total fermion number by 2, and vice versa. So now instead of conservation of spin polarization, you get conservation of spin polarization modulo 2. So we can go to the experiment and ask, can you actually see this process of pairs creating and annihilating? So I'll start all the spins down, shown in blue, and I can measure the average spin density. So it flips from down to up, so it depolarizes. But you could say that maybe something else is not working and things just depolarize. So how can I see this pair creation annihilation? So the way you can do this is simply by looking at the snapshots and looking at full counting statistics. I can just count every single shot how many spin-ups are in the system. Initially there is 0. As time evolves, I indeed see 2 and 4 and 6 actually emerge, but not the odd numbers. So this is sort of direct observation of this simple physics of SC mod 2. And of course, you could also show this, that this process is actually coherent. Spins can get flipped in pairs out of the vacuum, and they can also pop back into the vacuum state. So this entire process is coherent. So this gets me, so that's maybe all I want to say about this, since I'm at the end of my time. So I'll just sort of briefly summarize what I have told you in this talk. So what I've tried to sort of show you a bit is an incomplete survey of the different areas of quantum simulation that have been explored with these AMO platforms over the past 20 plus years. And this has to do with bulk gases of bosons, of fermions, and also Hubbard systems of both bosons and fermions. I told you a little bit about how one can manipulate these with laser beams and also with different types of magnetic fields. And then I told you about how this powerful technology of microscopically seeing every particle in quantum gas microscopes allow you to really directly see certain phases of matter and also get more information about these systems. And then I told you a little bit, very, very briefly, about how optical tweezer systems work and some of the powerful capabilities that you have. And then in this final little bit that I told you about on spin dynamics that we've been working on in our group, I tried to give you some examples of how these microscopic detection capabilities and this ideas of digital quantum simulation can really open new doors. Now, looking ahead, of course, in these lattice systems, one area is looking at strongly correlated fermions, new geometries, and at colder temperatures. With tweezer experiments, now we're actually entering the regime where experimentally we can now access the intersection between quantum information and also quantum simulation. So one very exciting area, definitely that will become experimentally possible, is asking whether limited ingredients like gates and ancillas and some limited digital steps can be combined to actually study many-body physics in these tweezer platforms. So with that, I'll end here, and I'll be happy to take any questions.
Thank you, Professor, for the talk. And we now have some time for any questions.
Except your talk, what's the time scale of the spin dynamics?
So in our system, the interactions are fairly slow. So these are tens of milliseconds for one exchange. But again, the thing I want to emphasize is that the states intrinsically can live forever. In our experiment, the coherence times are typically close to a second. And that's sort of technical. Fundamentally, there shouldn't be a limit.
thank you for the great talk. I have two questions. One slightly more technical. Can you explain again what is the mechanism for the pair loss?
So this actually has to do with so-called light-assisted collisions. So if you take two atoms that are very close together and you shine resonant light, this actually excites the atom into excited state two atom potentials, and they can actually gain a lot of kinetic energy. So when they decay back, both of them actually fly apart. And it just turns out that for these experiments, the two-body rate is typically fast enough compared to the three-body rate. So they always lose in pairs. So then if you have three, you still see one.
And is there any possibility to simulate a single component strongly interacting Fermi liquids? Yeah, I mean the Feshbach resonance method you described require two components. Do you see any possibility of simulating?
Yeah, so I think the short answer is yes. So I told you earlier that at low temperatures, typically only S-wave interactions are present are relevant, and you need spin up and spin down because they're fermions to have any type of interactions. Now that's not quite true because with a single component Fermi gas, you can actually get P-wave interactions. And there actually, many years back, people have looked at trying to go near a P-wave Feshbach resonance to see if they can actually get strong interactions. Now, typically near resonances, you also have to deal with loss, so that doesn't quite work. Now, there is actually another exciting area that I didn't get to talk about that has to do with molecules, not in tweezers, but actually as bulk gases. So there's actually been a lot of recent advances of bulk gases and molecules, whereby now people can create degenerate BCs of polar molecules and also of fermionic molecular gases. Now, if you have fermionic molecules, find the molecule slide, maybe this thing. If you have fermionic molecules, then that are polar, they can still interact via the dipolar interaction. So this means that the P-wave scattering need not be small anymore because the dipolar interaction can be strong. So one of the big goals for fermionic molecules in bulk environments is to actually reach P-wave superfluids. Temperatures are currently still a bit high, maybe a factor of 5 higher than where people expect in optimistic cases where that would be. So that's sort of another avenue to single component Fermi gases.
And in principle, one can, I know attractive is more interesting, you get P-wave superfluid, how about getting repulsive interaction? Is it also a possibility? Usually.
Yeah, I would say on paper, there are always ways to engineer the model. With the molecules, it's a little bit tricky because it's actually hard to predict whether you'll get losses that you don't like. But in principle, the scattering should be tunable, repulsive and attractive.
That's very impressive. And I wanted to ask, what are you showed a one-dimensional system of 8 or 9 molecules, and what are the limitations to go to bigger systems and higher dimensional systems?
So that's actually a direction that we want to move in. Currently, the limitation is, I would say, laser power. So each trap requires some power to create, and we have a finite amount of laser power. But that is sort of a purely technical limitation, because fundamentally, there's no reason that we cannot create as large of an array as an atoms, which by now are in the thousands. And one of the, maybe I'll give one more explanation. I told you earlier that the energy shift due to a off-resonant laser beam goes as 1 over the detuning. So we're using a fairly large detuning, about 10 times larger than what people typically use for atoms due to various reasons of molecular structure. But one can, always try going closer, and for the same power, it will give you effectively 10 times the trap depth, meaning you could have 10 times the number of sites easily. Currently, we can do something like 50 sites or so.
If there's no more question, let's take the speaker again.